Hello! Welcome to the Berkeley Seminar. As usual, we have an incredible, as 75% of the time usual, we have an incredible speaker, and we're going to do our, the other 25% of the time we do lightning talks, and we have five incredible speakers.
They're sometimes bad.
Yeah. So, as usual, please help us make sense of the talk. You can make sense of anything. It might be the technical details. It might be Kevin's motivation. It might be something in the connection between like what you care about and what Kevin cares about. So to introduce our speaker is our very own Kevin Carlson. A couple weeks ago, he gave a lightning talk about double functors, which was super cool. But of course, a lightning talk is only 5 minutes, and it turned out Kevin had, in fact, 60 minutes of things to tell us. So we're going to finish up here and learn what is it like to be a lax double functor. Take it away, Kevin.
Thanks, Sophie. Thanks, everyone, for being here. The idea today is to try to get across somehow some of the core ideas mathematically that are running our new CatColab software and are the reason why it's going to be what it's going to be. It's a very interesting situation because there are some quite deep, quite new category theoretic ideas that are right in the heart of our software. You've seen, many of you, a couple of talks about CatColab itself recently, but most of you won't have read Evan's several hundred pages worth of double category theory that he's published in the last year. And so I wanted to see whether I could get across some of the core ideas of how it is that we're building some cool practical software that non-category theorists can use, but that it actually relies on this hot off the presses category theory. As time allows, I'll tell you about a little something new that's not in all of Evan and Michael Lambert's work. So the reference for most of this is going to be Lambert and Patterson Cartesian double theories. And then if we hopefully make it down here, the reference will be the dev docs for CatColab. We have a forest there. So I know there's a wide range of familiarities with double category theory in the room. Some of you have written 300 pages on it in the last 2 years, and some of you may be hearing the word for the first time just now. So I'm going to try to both not leave you behind in the first 3 seconds and not to get bogged down in too many fundamental definitions by mostly drawing illustrative pictures. But please stop me, especially early on, as much as you want to try to make sure you're getting something out of what I'm trying to say. So double category, I am going to assume you know basically what a category is. Hopefully I can get away with that. So a double category is the kind of thing that has objects and vertical arrows. You're going to be able to compose them so far you have a category. There's another kind of arrow that we draw that way, usually horizontally and with a little dash. And connecting these two kinds of arrows, there are these square-shaped cells.
So is this like the category of functors where it's strict in one direction and weak in the other?
Yes. Yeah, the composition, you can compose all of these things in any way that you could like stick a bunch of those glyphs together. You can compose the result. So you could stick 3 of these squares next to each other and compose into one square, or you could stick a couple of these horizontal arrows next to each other and compose. But the key thing is that those arrows compose strictly associatively, so you have an actual category in that direction. This composition is weakly associative, so if you know about bicategories, what we basically have is a category in this direction and a bicategory in that direction, and they interact via these squares. So for instance, the double category of spans of sets has objects, sets, vertical morphisms, functions, horizontal morphisms, spans of sets, which means a third set over x and over y. If those two morphisms from that third set that I haven't named are jointly injective, monomorphic, then this is a relation. So this could be, for instance, a relation, and squares are maps of spans.
So do you want T to be at the apex of that span?
You could abuse, that would be a slight abuse of notation, but actually that's probably a pretty good name. So there's also these projections that come in the data of giving a span. But yeah, that's abusing that notation probably makes sense, thank you. And squares will be, if you try to figure out how you can map two spans to each other, you'll find yourself wanting to draw a commutative tent like that. So this is the most fundamental example of a double category. Spans, I should really just write span. I think I wrote that extra S from auditory interference. Span serves the role for double categories that the category of sets serves for ordinary categories, which is to say it's a good location for representable functors. It's kind of what you're always mapping into. And I won't draw pictures of this right now. Maybe I should. If you want to compose two spans, you will find why we have this weak notion of composition. You have two spans in sequence. The way we'll compose them is by taking a pullback like so, and then you can compose those two sequential legs on left and right. And if you think about what happens when you take iterated pullbacks, you'll find that composition in spans is not strictly associative. So we really don't have a category in this direction. So, but the span is a place that you can have functions, you can have relations, and some more general stuff. They all play really nicely together. Sometimes you want either of those objects, and that's a little bit of a hint of what's cool about double categories. Anything I can clarify up to there? Just one more example real quick that we'll see. Prof is the double category of categories instead of sets. Functors as the vertical or type morphisms. Profunctors, which are families a profunctor between two categories is a family of sets that the categories act on either side. A presheaf is an example of a profunctor. We'll flesh out in 30 minutes when we get back to instances, if that's unfamiliar. But so there are double categories of sets, double categories of categories. They're both great. In some sense, these capture more of set theory and category theory than any one category or two category or bi-category of these things you can build.
One quick question.
Yeah.
In pure set theory, could I have the thing just be a binary relation from x to y? And then the mapping means if two things are related, then their images are related?
Absolutely, yeah. So there's a sub-double category of span on just relations, and then there's at most one cell filling any square just using the partial order on.
More associativity there.
Yes, yeah. By taking the image, you can make that be strictly associative. Thanks. Any other questions? Okay, so that's kind of the, what else did I say there? Theories, doctrines. In CatColab, the data structure that we study, and if you've never seen CatColab, especially if you're bored or something, you might pull it up, catcolab.org, and look at something to have a little more visual. So CatColab is based on double functors, technically lax double functors, from some double category into this category of spans I just mentioned. But these double functors can be of various kinds. And so I'm going to completely ignore the notion of doctrines for almost the entirety of the talk, but mention that there are doctrines, because a lot of the richest examples come in doctrines that I won't be discussing today. So the simple doctrine, which we'll be mainly studying, is D is just a plain double category, and we'll talk about lax double functors from D into span. Another doctrine we're working right now is the Cartesian doctrine, which is a central topic of Evan and Michael's paper. There's a good notion of products in a double category. You can ask for product-preserving functors, and many interesting examples are there. And then this is just for the fans. The only other doctrine that's actually in the main branch of CatColab right now is tabulator preserving. Call that the tabulator doctrine. And there's tabulators are some kind of cool double category construction that reflects how to take a relation, for instance, a construct its graph. There's some universal property in double category of this kind of construction. So there are lots of different versions. Sorry.
Vertical thing to horizontal?
No, from horizontal to vertical. Let me not actually draw the right picture right now. There's something about connecting the horizontal to the vertical that's useful. So how CatColab basically works is there's many different interesting things that you can make be D in various different contexts of kinds of double category theory you might be doing. And we let you build models, lax double functors, out of such various examples of and flavors of D that you can do your scientific world modeling in. So let me stop with the generalities in section 0 there. Anything else first?
So it looks like if you take prof to be D, you could write down the theory of a Cartesian closed category, because you can express the Hom tensor junction using the profunctor.
If I take prof to be D, the domain is
D to
usually
be prof.
yeah. The domain is going to be something tiny. Usually, like if D is a point, I'll say in a minute, then a lax double functor will be a category. Taking D to be all of prof might be interesting.
I'm
But
sorry,
okay, so there was some kind of inversion.
So
Yeah.
there would be a theory that would be whose models would be prof
Cartesian.
rather than
Yes, yeah. So the question of taking models in prof is very central and interesting here. Being able to construct a theory whose models are Cartesian closed categories is still an open problem that we think has to do with understanding the notion of compact closed double category, that the theory might need to have some duals in it. Okay. So again, all these words go away for the rest of the talk. We're just going to talk about what we can do with lax double functors from a small double category D into span, simple doctrine, and see what that means and how these definitions give rise to something that to a theory that's inherently compositional in a way that you really need the double category theory to accomplish. Okay, so let's take what I will proceed to mostly define this is now catching up to my lightning talk from last week. So what's the structure that this has? First of all, okay, so if you look at a double category and you try to get some kind of a functor notion out of it, some of the things are going to come likely pretty intuitively. You're going to need to map all the stuff that's in D into span. There's mappings on objects, tight arrows, loose arrows, and cells. So for instance, if you have a cell like this in D, then that's going to have an image in span. So remember, we've defined these horizontal arrows. That'll be an actual span of actual sets with a map between those spans, or maybe a containment between the relations if the spans happen to be relations. Okay, so that's a start. And if we were just talking about functors between categories, that would be basically it, right? A functor between category just has a mapping on objects and a mapping on arrows, and then there's some properties. So if you guess that it's something like this and then there's some properties, kind of the central point of this talk is that you will think incorrectly that a lax double functor into span is like a bunch of sets shaped like D with some functions and spans or relations between them. And that is actually a complete misconception of what X is like, what it's like to be X, shall I say. And if you think that, you will misunderstand something right at the heart of how CatColab works. So what else is there? Does anybody who was here last week remember what kind of other structures I'm about to give? I'm sort of curious because I'm semi-repeating myself, and I'm assuming you maybe don't remember. Compositors and unitors, yeah, are the key other things. So the laxity of the double functor means by definition that there's this further structure called compositors and unitors that has to do with the fact that the composition horizontally is not strictly associative. And so that looks like if you have a composable pair of horizontal or loose arrows, I keep switching between horizontal and loose. Horizontal is semantically vacuous, but as long as I draw them horizontally, it works. So if I'll use this notation for the composite, horizontal composite of two arrows, because I don't know, it's a kind of weird composite. If I have a diagram like that, I'm not going to say, that my model X maps the composite of P and Q exactly to the composite of where it maps P and Q. In a double category, if I try to, so I kind of drew this like I'm in a bicategory or something. In a double category, I'm going to end up drawing a picture like this, and it's actually sort of unnatural to be like, let's make that commute. The most natural thing is to put a cell in. And indeed I will. That's the cell called the compositor. So there's a map from the composite of the images to the image of the composites. This is the same kind of thing that happens in, say, a lax monoidal functor, which is some like shifting down a couple levels of that. And something similar for units that I probably won't draw. And why is this interesting? That's the key thing I'm attempting, hopefully not too quixotically, to get across, is why is this little bit of technical abstract whatever, why does this do something interesting for our software? And so the reason is this. There's a special case of this we'll always be able to do when x equals y equals z and p and q are the horizontal identities of x and y. I'm going to write u instead of id for the horizontal identities. There's also vertical identities. So in the case of the double category of spans, the horizontal identities are just the identity spans, x to x to x. So what happens when we consider the Laxer for that composite? After applying x, we're in the category of spans, so I'm going to draw actual spans. No, no. So that's the abusive notation that Mike was suggesting for the image of the horizontal arrow, ux under x. So big X maps ux to some horizontal arrow in span. So I'm drawing it as an actual span.
Sorry, I thought ux was supposed to be the identity.
No, you didn't write the uniters, but it's
Oh,
uniters.
these are the uniters.
No, I'm doing the compositor of the unit.
Uniter is U is the uniter, right?
No, U is the
No.
identity span.
U lives in D.
Thank you. Yes, this is, there are many things that are many kinds of identities, and yeah.
X of UX is okay.
Okay, so this is in D. Ux is the horizontal identity
Yep.
of the object X. All right, that picture's in D.
Yep.
Let me do this in 2 steps. No, thank you. I think that everyone had a slightly different conception of what I was drawing. Okay, so if I map this diagram in D under the Lax functor X,
My question is, doesn't ux have to map to the horizontal identity in span?
no.
No. Okay,
Right.
so
That's the uniters say something like u of x maps to x of u of x. So maybe I should have drawn those after all. Right. So the existence of uniters is critically related to the fact that this x does not quite preserve the horizontal identities either. Thank you. Okay, and so there's a compositor like this. The composite of ux with itself in D, though, is ux under an assumption I'm making that if you already know what it is, you already know what it is. Okay, so there's a compositor like that. All right, now, so that's just applying x for not remembering we're in span yet. So, okay, what that actually means in span is I've got some set. Everything now I'm drawing will be sets and functions and sets. Okay, I'm decompiling this all the way. I don't think I'll need to name that. Which way should I draw this? Something like that. Okay, so as we had defined it, I think I've erased it now. The cells in span are given by commutative diagrams like that. So this pullback is composing these two things in span, as we said. And there's a cell in span that's that function there. So let's decompile this a little bit further. Let's name. Notice the same span is happening 3 times in that diagram. So I'm going to very suggestively name the legs of that span from x to the identity s and t. You just look at this span on its own. A span with the same base on either side, that's just a graph. That's a directed graph. So I can understand what this diagram means by actually drawing its elements. At x as vertices and its elements at ux as edges. So I have a graph just from the bottom of this before I even got to the compositor. So actually, that's already kind of interesting. And I could have said that in a separate step. The existence of horizontal identities means that this functor that I sort of thought was going to be valued in sets is already valued in graphs. So there's more structure than you expected. But now the compositor is giving a huge further level of structure. I will want a name for this. In this notation, this pullback Q is the set of all triples of vertices in this graph and pairs of edges. It's the set of all paths of length 2 in this graph. And I have a map from Q back down to the set of edges. Which commutes with taking the source of the first side or the source of the image, or taking the target of the second leg of the graph or the target of the image, that commutes. So this map has to behave like so, sending such a path to another edge, H, and we'll just define that H to be the composite F and then G. Maybe I'll say to be friendly, or G of and then F. The compositor of this lax double functor at horizontal identities provides a composition structure to this canonical graph formed on every value of x. X is not just valued in sets and functions and spans, but so far, x is valued in graphs where you can compose paths, which is
Where you can compose edges.
I'm just composing the same way as in a category.
Yeah.
Yeah. Mm-hmm. I can compose pairs of adjacent edges. Mm-hmm.
It's just, that would be necessarily a closed graph in the sense of if you have F, if you can reach from A to B and from B to C, there must necessarily be an edge from A to C.
Yeah, yeah. So I've got a graph with some kind of like transitivity property or something now. And okay, obviously, I won't want to say many more technical details about exactly why the following is true, but you maybe won't be shocked to hear that various axioms of lax double functors that I haven't written down will come together to say that, oh, this graph with a composition of some kind turns out to actually be a category.
And is the general case of bipartite graph?
There's nothing bipartite here.
Okay.
The image of...
Not this particular case, but when you're not doing an identity span.
Oh, sure, yeah. So if you apply to different horizontal arrows, then yeah, you'll get bipartite graphs, and then they've got some sort of partial composition operations on them or something. Yeah, that's right. But focusing on this gives you the core idea, I think, which is that the magic of laxness of compositors means that every time you build anything in CatColab, you're building a lax double functor, little do you know it. And so you'll build some little model of something, you'll build your little stock flow diagram or your ontology log or something like that, and the math in the background, in the Rust, knows that you're not, though you're visualizing probably just the graphs. That's what the visualization in CatColab basically does. The software knows that those graphs are actually categories and you can actually compose in this model. And that's really at the heart of the value proposition of CatColab. So there's a theorem, just to sort of put a bow on this. So you know what precise result I'm showing off a couple aspects of. Lax double functors like this are actually the same as lax double functors, which preserve those horizontal units into prof. You preserving, I mean these things, these horizontal units. So yeah, there's some normal lax double functors. So there's some cool theorem, which I've proven 5% of, that if you take a lax functor into span, which is kind of easy to think about because it's just a bunch of sets, sort of, magically you're actually taking a functor into prof, into the double category of categories.
And that functor was Mike's bipartite graph.
Yeah. So that you get a bunch of profunctors that are that's the like horizontal categorification of those bipartite graphs with various actions. So that's what you're really touching anytime you build something in CatColab. And I would like to try to draw one picture of what that means before trying to say a few words about instances. Any questions on this? Do people who feels like they got an epsilon more of what it's like to be a lax profunctor from that? Anyone? Cool. That's not bad. That's not bad.
So,
yeah.
This theorem, like you did it
Yes.
time, but
Yes.
like actually
Yes.
like, okay.
It would be impossible to prove in a talk, of course, but it's actually and it's actually like this stuff. There's nothing very hard over there. This is actually not that easy of a theorem. There's many more steps, but yeah, it's good to know it's there.
But you say you've only improved a bit of, like you said you proved 5% of it. You personally.
I write now in this talk.
Okay.
I don't know actually who it's in Lambert Patterson. I don't really know who I should originally cite it to. It's got sort of a long prehistory, starting with the fact that a lax functor out of a point into a bicategory is a monad in that bicategory, which is probably 50 years old. So, but yeah, that's a thing.
And can you repeat the thing we should add?
You should not think that a lax double functor is really just a bunch of sets.
Okay, yeah.
You should really think that it's valued in categories. But if you need to prove something about it, it might be fun to remember that you only really have to think about the sets as the basic codomain. Anything else? So let me just draw this little picture over here. Yeah. Yes.
Okay, you tell me, I'm like, I can just think about it as a bunch of sets. But if I'm actually giving you the lax double functor, then I have to give you the compositor and uniter, which is all the other stuff too.
Yeah.
So
Yeah, I mean, they are equivalent. So things that are the same are in some sense the same as each other, right? There's no like magical disappearing work. Yeah. But yeah, if you're trying to write one down, like, I mean, we really do.
Oh, I shouldn't stop at mappings on objects.
No, yeah, you probably won't give a full definition that way. But actually, in CatColab, the models that we actually build are freely generated from the graph level. So you can stop sort of partway and then be like, do a left adjoint or something. So one.
And
yes.
the categories you're dealing with will be small necessarily because these are.
Yeah. I mean, in the software, of course, they're finite or finitely generated, and yeah, we're imagining small. But you could do stuff if you really wanted to. So an example that's just a hair less trivial than the simplest possible is consider the small double category that's got a z mod 2 of vertical arrows. Those don't look very vertical, but I didn't cross them, so that must be what I mean. Then its models are called signed categories by.
You want the horizontal Z2 in the horizontal direction?
Wait a second. Yes, yeah, I don't want categories. I do want the horizontal one. Yeah, thank you. That's a cool thing too, but no. That would be categories within involution. So that's called, at least in the dev docs, signed categories. So what they look like is they're a lot like a category, except they have some morphisms that are positive and some morphisms that are negative. And the composite of, what am I going to want here? I'm going to want a loop. And the composite of two negative morphisms must be positive. So that's the Zmod 2 multiplication table coming in there. So that's a cool kind of object. That's an example of how we can immediately start enriching a little bit beyond plain categories. We use this in CatColab to model causal loop diagrams, which are a diagrammatic language widely used in systems dynamics. So this kind of diagram would say you've got various things x, y, z, and w, and like if y happens, it tends to encourage x to happen more, but if x happens, it tends to discourage z from happening. So it's a very simple qualitative kind of systems dynamics modeling, but people use it to get their head around big, complicated policy and modeling problems very frequently. And they don't realize they're talking about signed categories, but they are. And in particular, what I've drawn here, other than maybe saying that the composite of those two minuses is supposed to be a plus, I've basically just drawn a signed graph, right? A graph with some pluses and minuses on it. But in the math and in the software, and in the practice of systems dynamics traditionally, it's very, very important that this is not just a signed graph, that it's a signed category. Because there's a homomorphism I'll just do this atemporally. There's a homomorphism from the signed category to the signed category generated by a single positive loop to this thing that loops all the way around. If I name those four arrows, I can map A to K after H after G after F. I can send this loop all the way around that graph, which is something you can't do for maps of graphs, right? You need the composite structure to say that's there. And that's a valid homomorphism because if you compose two negatives and two positives, you'll get a positive. And looking for homomorphisms like that is a central activity in systems dynamics when they look at causal loop diagrams. Because what that tells you is that if you go all the way around that loop, it's positive. That's called a reinforcing feedback loop. That says that by looping all the way around, doing more x tends to eventually indirectly cause more x. So without any kind of quantitative modeling to this, this is a picture of a situation where x will tend to run off to infinity over time without anything else interfering. And that's a fact about homomorphisms of signed categories. Yeah?
I have this desire. I'm like, can you go slow and explain to me? So I'm like, what I got from this is I'm like, great, for every point, I'm going to think now I have a category. And now you've added one more morphism.
Okay, yeah, so right. The typing of this is probably maybe not clear. But sorry, finish your sentence.
Oh, no.
Yeah.
Can you tell me, so the single dot with just the one morphism. Sorry.
So this is one, let's call this x. This is one model of this theory. So this is some functor from this, Lax functor from that to span. And how do I know it's a Lax functor from that to span? Well, it's a signed category. It's like the terminal signed category, I guess.
Are you wanting to know like where the composition laws come from? Like why is
I'm not quite sure. So, sorry. So, I'm assuming I have a model of D.
Mm-hmm. And we have two,
And we have
if you trust what I've drawn. Mm-hmm.
the arrows with the plus on them
Uh-huh.
come from the identity
Right.
morphism in D.
Mm-hmm.
And the arrows with the minus on them come from the Z mod 2.
Yes. Yeah.
The other morphism in D.
Mm-hmm.
Can you explain to me
Yeah.
one other thing?
Yeah. So there's this horizontal Z mod 2, and if you believe this theorem, yeah. Thanks. That's a very good question. I was totally skipping over something interesting there. If you say the generating horizontal morphism there is Q, then x of Q is supposed to be a profunctor from x of dot to x of dot. According to this theorem, right, x of dot is an actual category, x of Q is an actual profunctor between the endoprofunctor of that category. So you can draw profunctors using heteromorphisms, and the illustration I'm using for that profunctor is just I'm marking the heteromorphisms negative.
But even without using that theorem, can we see like the compositor that gets used to do?
Sure.
Like that. Yeah.
And since there's supposed to be a z mod 2 of endomorphisms here, q squared is the identity. So that's answering basically a separate half of those. This is, I haven't touched any uniters the whole time. X of u is the positive arrows. That's kind of what we're doing. Yeah, but you don't. The uniter that I haven't ever mentioned gives you the identity morphisms in the category. But so this is the compositor for q. Since q composed with q is the identity of the one object, I have a compositor like this.
So it takes any two negative arrows that compose and gives you a positive arrow.
Exactly.
Thank you.
Yeah, so even without having the whole theorem, you can see how by choosing P or Q in the compositor to be either the identity or Q, you get all the different combinations.
Right.
Cool.
Right.
Thank you.
I think you made a slight typo. The thing on the left, X, is not it's the free one, not the terminal one. The thing on the
Yeah, that's right. Yes, the freely generated by one positive morphism. Thank you. I made a speako. I didn't write it down, so it doesn't count. Great, cool. So yeah, that shows a little bit more how all of the behavior of a signed category really is packed into that lax functor. And then from this, just turn a crank, which we can turn in zillions and zillions of different examples, and you produce this feedback loop theory. Another thing, David?
Well, I just had a sense-making question.
Yeah, please.
If you took the monoid of, say, real numbers instead of z mod 2, and then you put like a less than as like some cell,
Uh-huh.
or equal to,
If I put less than or equal, so the real numbers are horizontal, and then I can put cells. Yeah, I can put globular cells for sure.
yeah. Would that be like weighted categories or something?
And right, it's the monoids of the composite is sum, and so so then I would get. Do I need the cells there? I'm not. I could also do
the reals. Then I'll have to when I compose two arrows, I have to get
the exact sum. So yeah, so you should get either if you don't put cells, if you just have the strict horizontal category, you should get weighted categories where the weight of a composite is equal to the sum of the weights. And if you do put the cells, you should get laxly weighted categories like you. So roughly the same, maybe the same as Lavier metric spaces if you take 0 to infinity.
Okay.
Yeah. Thanks.
What are the practical consequences of trying to put something like that in software?
With the reals, well, I mean, it does require. In our software right now, D needs to be finitely presented in some appropriate sense. Now, in the doctrines that I erase, you get some more powerful notions of finite presentation, like a Cartesian theory can have infinitely many objects as long as they're all products of finitely many. But R is really big, of course. So yeah, you need some kind of thing where you can have a whole type. A whole data type of generators, and there's no reason in principle why you couldn't try to do something like that. I think we can define a category like that right now in the Rust, but I doubt. I'm not actually sure how close we could get to instantiating a model of such a category right now.
I mean, I think we're going to want to do various things like that, like have a theory that might have, infinitely many, like for all real numbers or something operations, but that just requires building some special infrastructure to let you say that, well, for any choice of a number, we get a thing like that, and as long as you can give like, it's like in logic when people talk about like a axiom schema or something, which is finite, even if it generates infinitely many axioms, right? Like we will end up probably doing various things like that.
Yeah, you just need some nicely parameterized family. So it should be plausible.
Yeah. It's not a crazy thing.
Yeah, so that's pretty close to my time. I'm going to have to probably only say a quick hint about section 2, unless anybody wants to just keep asking about section 1, and section 2 could be part 2 or something. Okay. Right, so that's a little bit of what it's like to be a lax double functor, but what can they do? It's kind of like being a family of categories in some way. So can you do all the things with lax double functors that you can do with individual categories? Yes, pretty much, for an appropriate sense of all the things, I guess. So the content of Lambert-Patterson, which is 100 pages long and very detailed and full of great examples and technical arguments, but if I can summarize the contents in one sentence, it's that lax double functors like this form themselves a double category that should probably sprinkle in a word virtual there if I'm going to be really picky. And so if we think that a lax double functor is some sort of generalized category or family of categories, there are vertical morphisms that are certain kinds of families of functors between the categories that are all the values of x and y. And horizontal morphisms, which Lambert and Patterson call modules, that you can think of as families of profunctors between the values of x and y, which are lots and lots of coherence and nice things about how they all interact with x and y themselves. But that's kind of the very most fundamental idea. So you do have some kind of double category that's sort of generalized in the double category prof. But there's an interesting wrinkle, which is that, so I only said, I think, basically out loud what a profunctor is. If you're not deep into this game, it may be a very unfamiliar object. But the most important profunctors probably 75% of all the profunctors actually have domain or codomain the terminal category. And these are just so that I can actually define this case at least. If C is a category, plain category, a profunctor from 1 is a functor from C to set. A profunctor to 1 is a functor C op to set. I guess I should say that. So profunctors between categories in general generalize presheaves and co-presheaves, which are the most central concept of category theory in a lot of ways. So you might hope that these are called, again, modules or maybe bimodules. You might hope that modules x to 1, where 1 is now some terminal object in the category of models, generalize, in this case that would be presheaves. That would be great. But in general, they don't. So Evan noticed a few months ago that if you just write down the definition, specializing y to be terminal, this is what I think I'm out of time to communicate concretely, but non-concretely, if the theory D has some non-trivial horizontal arrows, then just writing down the definition of this gives you some kind of family of profunctors that one can act on non-trivially, which gives you some big, complicated, floppy, nasty thing that is not an instance of anything you ever heard of before. That I could draw at least for those who are kind of up on some of this, I could draw a picture of what exactly that means kind of quickly, but maybe ask me after if you want. If this is getting into the Cartesian doctrine, but if D is the theory whose models are multi-categories, and you look at a module like that, you get a multifunctor into the category of augmented simplicial sets. Whereas what you probably wanted to get was a multifunctor into the category of sets. That is the most natural generalization of, well, co-presheaf for multi-categories. So the one new thing in here is that we can pin the action of one in a certain sense to get a definition which is a like non-full specialization of the definition of module. We can narrow the definition of module, or there's also a definition from scratch that was Evan's first suggestion that is equivalent and works very well. And that gives us a common generalization of presheaves and co-presheaves, multi presheaves and co-presheaves. That's what I was saying about multi-categories, monoidal presheaves and co-presheaves. And very relevant to our interests here, attributed C-sets. A schema is a model of the theory that's generated by one horizontal arrow, and its instances in the naive sense don't work right. That's the simplest example. Schema is the simplest theory where it's just plain modules x to 1 don't work right. But if you take this pin definition that I've got in the dev docs there, then the instances really are atchits, which is great. That's the core data structure in our algebraic Julia ecosystem that we use for categorical database theory and various things, if you haven't seen it. And so that's cool. So instances in this sense are going to be kind of, depending on how you count, the third or fourth leg of the stool of CatColab. We've got doctrines, which are sort of floating around in the background that give you a big, huge, very, very meta sense of what kind of model you're building. Within a particular doctrine, you can construct a theory D, such as that. Once you've picked a theory, you can construct a model, such as that. Once you've constructed a model, you can construct an instance. And this is actually populating those abstract slots, X, Y, Z, and W, with some actual dots that might move around according to those arrows. And in various contexts, we know a lot about these things. And I'm particularly curious now to think about the theory of monoidal categories and symmetric monoidal categories, because I believe that if you take an instance of a model of this theory, thinking about it as a Petri net, then you are doing something that, let me just say, is closely related to the token semantics of Petri nets, which is its own whole big, huge theory that has kind of only one category theoretically informed paper about it, and would be really cool and interesting to say something about in a very different direction than these better known examples. So I think I will stop there and take any other questions. Thank you. Good question.
So I'm trying to figure out what, if you have an exact definition of an instance yet.
Yes.
An instance
Yes.
is just like a morphism from a model to one.
Right. So a module is defined at the very end of Lambert-Patterson, and so there's a notion of module into one, but it is not quite the correct definition of instance. But we do have a definition of instance, both as a special case of module, where you insist manually that one acts trivially in an appropriate sense, and also an elementary definition that says an instance is like a bunch of co-presheaves on all the values of x that relate in various nice ways.
And Kevin showed that those are equivalent.
Yeah, yeah. So you can see those two definitions and an argument that they're equivalent in the dev docs if you look.
I think do you have an answer to Mike?
I'm going to try.
Okay, yeah. Is that okay?
That when you look at lack double functors on the span, which is the subject there's a lot of them, and they form a virtual double category or something. So you have a notion of horizontal arrow between them. But when you unpack what that means, it's like X is a bunch of categories of profunctors, Y is a bunch of categories of profunctors, and this profunctor between them is like a bunch of, like, a matrix of categories of profunctors, an X by Y matrix of profunctors or something, ish. And so, like, if you take the terminal guy 1, which sends everything to the terminal category, then what is a profunctor there? It would just be it would be a 1 by C thing of profunctors, which I guess, maybe I made a mistake somehow, but it's something like a C set.
I don't know. There's a bunch of C would be like one value of X or something, right? So there's a C set, an X of X set for each object.
So a C set for each C in your schema Y.
Sure, sure.
Okay, and they'd be somehow related. But if C was small also, if he was also a one object doohickey, then like if capital D for C was a one object, then C would just be one category, and you really would get a presheave. But then something is a little floppy when you look at something, and there's a way to fix it that Kevin found.
Cool. Maybe a question I have is, okay, so I'm like, yeah. When D is the trivial double category.
Terminal, yeah.
I'm like, great, now X is a category and a module is a C set.
Yeah.
Okay, what about when D is that guy?
Is that?
So let's make it just one step harder. What happens?
So you want to know instances or a module between them?
A instance.
An instance is then,
It's gonna be a
what is it? It's a copresheaf on the sign. Right, so a model is a signed category.
Okay.
An instance is a copresheaf with an action of this profunctor. A copresheaf which acts on this profunctor in a way that you maybe could guess if you tried to write it out. There's a copresheaf on the category X of dot, and then there's this profunctor X of Q.
So it'd be like a database.
And yeah, so there's a database, and
Oh, but with two types of
Column?
and there's an action cell like that.
columns.
Yeah.
Mm,
And then
Do I think-
the negative signed columns, if you follow it twice, you get a positive signed column. Is that right?
do I think that? I'm not sure I do think that. So because I feel like I've only got one database, and then.
There are two kinds
Yeah.
of foreign keys. Yeah, two
Uh-huh.
kinds of foreign keys. Yeah.
Oh yeah, right. There's two colors of yeah. So yeah, it's a database with positive and negative signed foreign keys. Yeah, absolutely. And then if I follow two, I get back. Yeah, thank you.
Yeah, so for some examples, we know what instances are and why we like them. For other examples, for example, I don't know whether instances are that interesting or not, but that's a thing.
Right.
It's a thing that's out there. Yeah.
In that case, I feel pretty confident you could come up with a case where that's reasonable. We don't even really know what an instance over a tabulator theory should be, so I really don't know what an instance of a stock flow diagram is, for instance. But I hope it's something about like actually putting stocks in the stock and like flowing them along the flows.
That'd be so cool.
I think we're out of time,
All
right?
right, I think we're out of time, so let's thank our speaker, Kevin.
Thank you.